I guess no questions. All right. My drawing got discombobulated. I don't know what happened here. And something got changed. This 0 should not belong here. I don't know what happened. Okay. Something got changed badly. Oh, we're talking about example 10. And it's going to be part of the lab, so we're not going to talk about example 10 here right now. We just, example 11, page 25. A student reacted solid magnesium with excess hydrochloric acid in a closed Erlenmeyer flask. An Erlenmeyer flask looks like this.
Professor, what unit is this?
We are talking about unit on gases number 18. Page 25, the same. You just started, we just did it up to example 9 here, and then example 10. So we are continuing with that. Gonna finish the example, and then you are going to do the lab. So this example 10 we'll be doing in the lab, so I said we are not doing that. Example 11. A student reacted solid magnesium with excess hydrochloric acid. Whenever there is a reaction happening, the first thing you do is to write an equation, write the chemical equation for the reaction. So we have that chemical equation here. She gathered the following data: mass of magnesium, volume of hydrogen. So hydrogen was produced. How much hydrogen was produced when 0.124 gram, 0.0124 gram magnesium was reacted with hydrochloric acid? How much hydrogen is produced? That's the question. And we need to find R. That's what we are doing. So everything else is given there. Measured how much hydrogen is produced, because you know the volume of the container over here. And because this is an ideal gas, the volume of the container equals the volume of the gas. So that's Erlenmeyer flask. And I had this little drawing here that got discombobulated, so I need to draw a little drawing over here. How do you do this? So you would have hydrochloric acid here. That's easy to do. Hydrochloric acid liquid, aqueous.
Professor?
Yes.
Can you start recording?
If you wish. Okay. Let me go back then.
This meeting is being recorded.
So in order to find R, we need to do the PV equals nRT equation, and we have to convert that equation into find R. So R equals PV over NT. A simple algebraic manipulation, that's all there is involved. R equals that, and you write down P, and you write down V, and you write down N, and you write down T. All these are given to you because the student did the experiment to find all this. So mass of magnesium is that. Now, where is that? There is no information about mass of magnesium over here. Besides that, magnesium is a metal, and this equation is about gases. You cannot put anything about a solid into the equation for gases. It must be gas. This must be hydrogen gas. The pressure of hydrogen gas, the volume of hydrogen gas, the number of moles of hydrogen gas, and the temperature of hydrogen gas. The number of moles of hydrogen gas. We can calculate that. Grams to moles to moles. Stop right there. Don't go to grams again. So we say, okay, we have the equation. We know how much magnesium we used. We have excess hydrogen here, excess acid here. So all the magnesium got used up, and it was the limiting reagent. So we know how much hydrogen can be made. We can calculate that, how many moles of hydrogen can be made, and that's the calculation we did over here. 0.0124 gram of magnesium, convert that into moles of hydrogen. And stop at the moles of hydrogen. For gases, almost all the time, we don't talk about grams. You don't calculate grams of a gas. What's the point of it? We have talked about how very difficult it is to measure the mass of a gas. I mean, it can be done, but it's very difficult. Anyway, this many moles of hydrogen was made. So we plug in that value, mole of hydrogen, right there. R equals PV over NT. N is that temperature was measured by the student, and it has to put in K, Kelvin, not degree Celsius. And here we have torr, and here we have liter, and that's fine. Torr and liter are given to us. If you want in atmosphere, you can convert that into the torr. This is the pressure of the hydrogen gas. This is the mass of the hydrogen gas, which equals the mass of the container. Thus, this container was 206.265 liter. Now that's easy to measure, because what we would do, we would put water into the container all the way. This would be closed like that. We'll put water in the container to over here. And then we'll put this water in a graduated cylinder and measure how much water there is in the container. So we know the volume of the container. And the volume of the container equals the volume of the gas under normal circumstances, under ideal circumstances. And so we have normal circumstances, therefore the ideal gas law is used, and the kinetic molecular theory is valid. Under non-ideal condition, we'll have to change the kinetic molecular theory, and we would have to change the PV equals nRT equation, but we don't have to do that now. So we just have to find the moles of hydrogen, which is stoichiometry. And now we are just going to plug those value in the equation, and the value comes out to be 62.7. And true value of R is 62.4 liters of mole degree Kelvin. So sometimes, as I have told you in the experiment, true values are given to you. Sometimes you already know them. True value is considered the best possible value that you can get. And how is it gotten? By many people doing many experiments, expert people doing many experiments and coming to an average. That's how the true value is established. And this is the experimental value. So if we want to, we can find out the percent error. And percent, you guys are getting good at knowing what percent is. Percent is part over whole multiplied by 100. And the error is going to be 0.3 torr divided by liter multiplied by mole Kelvin, this minus that. And the error is taken as absolute value, which I wrote down for you some other time. And if you have to do that again in the lab, I'll give it to you in the lab again so that you would know. So that we can measure the percent error here by that means. We're not going to do that, but that's what we can do. So here I'm explaining to you how to handle this type of problem, which is a mixed type of problem. We talked about three types of problems: non-dimensional analysis problem, dimensional analysis problem, and a mixed problem. The non-dimensional analysis problem involves addition and subtraction, because we don't do that in dimensional analysis. It also involves algebraic substitution, like we did in some other problems over here, and we'll be doing again. Algebraic substitution is not dimensional analysis. You're not changing, you're not going one unit to another unit or another substance. So algebraic substitution is easy. If 5 out of these 6 values are given to you, you can find the 6th value by algebraic substitution, and you know that. So that's something involves in a non-dimensional analysis problem. But if there are both of this in a problem, dimensional analysis and non-dimensional analysis, which involves either addition or subtraction or algebraic substitution, those are the 2 types of problems. Addition and subtraction is very easy. Everybody knows how to do that. Algebraic substitution is very easy too. You know how to do it. So it's relatively easy. Now you also know how to do dimensional analysis. Now it's just that a question that this problem has both of them in there. So that's what the question. And how do I approach this problem? I wrote it down. All this is written down for you to understand how to approach this kind of problem. So write the chemical equation. As I said, as soon as you see something reacted, you write the chemical equation. Now, for gases, there are 2 equations that are very important. There is 3rd equation. We'll talk about a little bit about that later. But these 2 equations, either PV equals nRT, ideal gas law, or combined gas law. These are the 2 equations. There are no other equations that you need to worry about in these units, 18 and 19. So you don't have to worry about P1 over V1, P1 V1 equals P2 V2. You don't have to be concerned about that, because that equation is inside here combined gas law. So that's why you don't have to be worried about it. So you just either say, which equation am I going to use? Am I going to use PV equals nRT, or am I going to use combined gas law? All these problems can also be done using PV equals nRT, but then you'll have to do a little bit more. So if you know combined gas law, it'll make a little bit easier for you to do it in that way. So this is the question. When you see a gas law problem, then you are going to ask yourself, am I going to use the ideal gas law, or am I going to use the combined gas law? That's the question. One more type of gas law there is that I'll talk about it a little bit later, but that's the most of the time this is the question. Now, in combined gas law, what's going to happen? Some values will be given to you and one value will not be given to you. So you have to find one value, and by just putting it algebraic substitution, that's all. And PV equals nRT. Number of moles have to be given to you. Then you can use PV equals nRT. If number of moles are not given, then you use P1 V1 over T1 equals P2 V2 over T2, because this means number of moles are constant. That's what that means, because you don't have n in here. That means n is constant, and here n may or may not be constant. Now, another thing to remember one more time, these are gas equations, so do not put grams inside the gas equation unless you are talking about a specific type of PV equals nRT equation, and we talked about that, how grams involves grams divided by molar mass equals gram divided by molar mass, m is molar mass, equals mole. So instead of mole, you can write grams divided by molar mass, and then you can find the molar mass of the gas only, not solids, not liquids, only gases. So that particular equation has grams in it. Otherwise, when we talk about gases, we don't talk about grams. So here we say, which equation am I going to use? Well, mass of magnesium is given to me. That means I can find the moles of hydrogen. That's what that means. So moles of hydrogen can be found. If moles of hydrogen is found, then we will be using PV equals nRT because now we have moles. This is when the moles are not given, they are constant. The universal gas constant R is part of the ideal gas law. So use ideal gas law. That's the other way to look at it. You want to find universal gas constant. Of course, you are not going to use this law because there are no universal gas constants in it, no R in it. So we don't have anything choice. So thus, we are going to convert grams of magnesium to moles of hydrogen first. And then we're going to plug in the values. All the values are given here. They're there. And then we got the answer there. Okay, example 11. Example 12. The volume of an air-filled balloon is 30 milliliter. The pressure of air is 750 torr, and the temperature of the air is 15 degrees Celsius. The balloon is taken to the bottom of a 9 feet deep swimming pool at 10 degrees Celsius. The pressure of the balloon air increases to 700, pressure is 768 torr. Because you have some water on top of it, the pressure is going to increase. Calculate the new volume of the balloon. The balloon volume is going to change because the temperature is different and the pressure is different. Now, which equation to be used? That's the question. Ideal gas law or combined gas law? Well, are we given number of moles or are we given grams that convert into number of moles? No, therefore we're going to use P1 V1 over T1 equals P2 V2 over T2. So that's the reasoning. Now, just once the reasoning is done, I'm just going to substitute all the values are given to me. 5 values are given here. 9 feet deep has nothing to do with this calculation. But the 5 values are given, so I write down the 5 values, and the 6th value, V2 is not given, so I find V2 by substitution. Okay. Example 13. Calculate the molar mass of a gaseous compound whose volume is 201.3 milliliter, temperature is 30 degrees Celsius, pressure is this, and mass is 0.582 grams.
Wait, I have a question, Professor.
Yes.
Can you go back to example 12? So what's T? What's T1? What's T? That's temperature. Does T stand for temperature?
Yes.
Okay.
And
how
one
is it-
stand for what?
And how is it 288 Kelvin? Where
Good.
do you see
But tell
288?
me first, what does this one stand for?
Temperature 1.
Initial temperature. Good. Temperature 1, initial temperature. And
Yeah.
what was that? 15. Right?
Where?
15 degrees, that's the initial temperature?
Oh, so you have to convert it from Celsius to Kelvin.
Yes, always.
Okay.
Always. Very good. Thank you.
Got it.
So here we are going to say molar mass. So it has to be PV equals nRT. So the first thing we do is to write down PV equals nRT. PV equals nRT. Now we say we have to calculate the molar mass.
I have a question. How do you know when to use the ideal gas law and the combined gas law?
Exactly. That is the most important question. That's the question you are going to ask all the time when there is gas problem involved. Now here we say calculate the molar mass of a gaseous compound. Molar mass, that means we have to have moles in there, right? So therefore it has to be PV equals nRT. The other equation, P1 V1 over T1 equals P2 V2 over T2, that equation does not have any moles in it, no N in there. So that's one way to look at it. If moles are involved, then you have to use PV equals nRT. If they are not involved, they are constant, then you use the other one.
Okay, and if you don't mind, can you actually zoom out the page?
Sorry, what?
Like zoom it out, like make it bigger? Can you do that?
Sure, I can do that.
Or just like open it big?
Oh, no, I can do that. Okay, that's better.
No, like I mean, like you can click on the green circle on top so you can open the full screen. Can you do that? Just the green button on top to open the full screen. Yeah, that's better.
You guys, you need to speak up. Thank you. Otherwise, how do I know? Thank you for speaking up. So PV equals nRT. This is how we decided that we were going to use PV equals nRT because it involves number of moles. Now, we say grams are given. So we have to convert this equation into the equation involving grams. So N equals number of mole equals, oops, I don't want to do that. Number of mole equals N equals grams divided by molar mass, and we call molar mass as mm. So instead of N, we are going to write down that. So PV equals grams divided by molar mass RT. Now we are supposed to find molar mass. So put molar mass on one side, put everything else on the other side. That's algebraic substitution. So molar mass equals mm equals GRT over PV. Now we just write down all the values that are given here for GRT. So we write down
You say it's 2RT? How did you get 2?
GRT.
Oh,
Okay?
G. Okay.
That's gram right there. So mm equals grams are given. This is the mass of gas. Very important. It has to be the mass of the gas. It can't be the mass of liquid or solid. That won't work in this equation. Only gases. So 0.582 grams. Oh, 582 grams. 582 grams. Multiply by R. Which R are we going to use? Pressure is given 754 torr. So we're going to use the R that has torr in it. That is going to be 62.4 torr. And I want you to always write down all units. So you're going to write down torr multiplied by liter, oops, divided by mole, multiplied by Kelvin.
Where did you get 62.4?
This is the R. We are substituting the value of R here. We're talking about this R here. This equation has R in it. What is the value of R? We want the value of R to be taken in torrs because we are given torr over here. So this is the value of R.
So the value of R is always 62.4?
If you are using the unit torr, R is a constant, you are right. It's a constant, it is always 62.2 torr multiplied by liter divided by mole multiplied by Kelvin. That's what a constant means, you are right. And this comes from what we did earlier. So then we have R and then we have temperature. And temperature needs to be converted into Kelvin, of course. So 30 degrees Celsius, convert that into Kelvin, and that's going to be 303 Kelvin. We just say 303 Kelvin. We do not say 303 degree Kelvin. Kelvin does not have degree in it. And then the pressure is 754 torr. 754 torr. Now, the important part is you should be able to cancel out all the units that you don't need, and you should be left over with the unit that you need. And which unit are you going to need over here? Molar mass is measured in grams over mole. So those are the units which you are left over with at that time. So let's find out when we cancel out. Torr and torr cancel out. Kelvin and Kelvin cancel out. Oh, this V, we need to write volume over here, down here. Remember this V. So torr multiplied by volume. And the volume is given to us as milliliter, and always convert that into liter because this is liter here. So 0.2013 liter. Liter and liter cancel out. Which unit are we left over with? Mole is in the denominator and grams is in the numerator. We are left over with units of grams divided by mole. And that is the correct unit for molar mass, grams divided by mole. Now we do the calculation. So let's see. 62.4 multiplied by...
Professor, is there any way you can maybe clean it up a little bit? Because it's really hard to read.
If I write in text, then I can't do this. So you'll have to make sure that you understand that. 0.582 grams multiplied by 62.4. I have canceled out all the units, so I'm not going to write units here. Those units that are canceled out. Okay, liter canceled out, torr canceled out, mole is not canceled out, so I'll have to write moles. Kelvin canceled out, so that's gone. Multiplied by 303 and then divided by 754. And I'm going to put this in the parentheses to remind myself that this is in the denominator, and I don't, just because I see a multiplication sign, I'm not going to multiply it. So that's going to be 754 multiplied by 0.201 point, oops, 0.2013 liter. And liter cancel out, so I'm not going to write liter here. And this unit is mole down below here. So mole, I'm going to write down there. Okay, now I'm going to do the calculation. Calculate that. Point 5.582 multiplied by 62.4 multiplied by 303 divided by 754, and then divided by, this is in the denominator, so we are again dividing by 0.2013. Okay, so what is the answer that you got? Anybody did this?
I'm doing it right now.
All right.
2.9378, and then you have to do it by sig figs. So 2.94.
2.94. grams per mole.
I guess 72.5.
How did you multiply it or divide?
Because the way that he said it was you divide. So when you do all the timesing on the top, you divide by 754 and then you divide again by the moles.
The way I did it was I timed 0.82 grams and then 62.4 torr times 303 Kelvin, and then I divided it all by 754 torr times 0.2013.
There's the problem right there.
You have to divide by both instead of timesing them together, I guess.
You have to divide again by 0.2013, not multiply.
Okay.
Now, one more thing. These are the two possible answers. Which one of these two answers would be correct without thinking about anything, by thinking of other things? What is the molar mass of hydrogen?
Wait,
Yes.
I'm sorry. Before you get the answer, I have a question. So when you write the equation out where 0.528 gram times 62.4 times 303, divide that by 754 times 0.2013 mole, and then divide again by 0.2013 mole.
Yes. Because this is in the denominator, and this multiplication is actually, you are supposed to multiply this together and then divide. So if we want to simplify this, we have to do this. 0.582 grams multiplied by 62.4 multiplied by 303 divided by, now what you're gonna do here, you're gonna multiply 754 with 0.2013. Do that. 754 multiplied by 0.2013.
So I got 151.78.
So you are supposed
You
to
got to put it in parentheses.
right 151.78.
78. Oh,
Not 78. You're right. 8, 7, 8, whatever. 7, 8, and that's now. This is what you have to do, right?
yeah.
Make sense? So
Uh-huh.
now you know what to. Now you will go ahead and do this, and then you will get the answer 72.5.
So I got 72.5.
Yep,
Okay.
that's right. Now we also think of this. Is there any guess? I mean, all these guesses that I'm giving you are real guesses, so they have to. I'm not going to give you something. If it is a hypothetical guess, I would tell you, but a guess cannot have the mass of molar mass of 2.94 grams per mole. Hydrogen has the lowest mass, and that's 2 grams per mole. And then the next gas is helium, that is 4 grams per mole. There is no other gas in the middle that could have 2.94 grams per mole. So if you get a strange answer like that for your molar mass, you're going to question yourself. Something is wrong here. Let me check care of this again. Then this is very important for us to go through here, this one here, because I saw that a number of you made a mistake in the quiz or in the exam. Instead of doing this, first you have to do this, and then you can multiply. But instead of doing that, you divided that, and then you got a number, and then you multiplied with that number instead of dividing. So that's what the problem is. So I'm glad that we have looked at that problem, and hopefully you won't do this again. All right. Any other question?
Nope.
And I wonder how many other students were sitting around there with the same question, but we're not going to ask. So you need to ask this person, you need to thank this person for asking that question for you, okay? You can do that in private if you don't want to do it in public. All right.
Thank you.
I embarrassed myself for your success.
Who? What? Well, yeah, I can understand that. At times I feel like I would embarrass myself if I ask a question, especially if it is a question that my wife has, and then it's something to do with mechanical stuff. And I think I have the answer, but she doesn't want to listen to my answer. She would want me to ask that question. I feel like that man who is working as a fixing this thing, he's gonna think I'm stupid or something. So I understand that. Yes, that does happen. And at times we are not able to overcome that. And at times we have to overcome that. So give yourself permission to overcome that once in a while at least, right? Example 14. A 4-liter balloon at 1 atmosphere pressure and 20 degrees Celsius. If the balloon is taken to the top of Mount Everest, where the pressure is 0.33 atmosphere and the temperature is negative 33 degrees Celsius. Texas wasn't that bad these days, but it was bad, negative 10 or something like that. Texas, negative 10. People died, no wonder. And did you hear about that? Their monthly bill, electrical and heating bill was $8,000 in 1 month. Think about that. What happened? How is that possible? Is this a democratic country or what happened? Anyway, we won't go into that, but it's a thing for thought. What would be its volume? Now, what are we going to do? We are going to say, are we going to use ideal gas law or are we going to use combined gas law? Do we see the mention of moles anyplace?
No.
That means what? Which law?
Combined gas law.
Combined gas law. PV equals nRT has moles in it. If moles are not mentioned, that means they are constant. And that's what it means, a balloon. A balloon moles are constant. We are not taking air in or putting air out or in. Okay. So then we write down PV equals nRT and then, sorry, P1, V1, T1, P1, T1, T business. So P1 multiplied by V1 divided by T1 equals P2 multiplied by V2 divided by T2. And substitute the values. How many values are given to us? 1, 2, 3, 4, and 5. Those 5 values, and the 6th value is unknown. The volume is unknown, so this V2 is unknown. So you are going to either write down everything and do your calculation, or you're going to say V2 equals. Then you're going to take everything else on the other side, T2 multiplied by P1 multiplied by V1. Yeah. Divided by P2 multiplied by T1. This is something I expect you to be able to do. This is a simple algebra, nothing to it. And I also have seen in the past with other classes, students tend to make a mistake with this, and I don't know why. Please, it's a simple algebra. Don't make a mistake like that. And then just plugging in these values over here. So it's a very simple question, nothing to it. The answer should be 9.8 liter. You can do that calculation later if you want to. Just plugging in values, nothing much to do. Example 15. A sample of a gas is stored in a container with flexible walls at 15 degrees Celsius. Aha. container with flexible walls like a balloon at 15 degrees Celsius. See, this is a balloon, so the volume can increase or decrease. If it is a rigid wall, then the volume cannot increase or decrease. Flexible wall at 15 degrees Celsius. A sample of a gas. That means moles are constant. Whenever you say a sample of a gas, that means you are not going to take in gas or take the gas out. Predict what would happen to the pressure of a gas if volume of the gas is decreased and the temperature is increased. Okay. So we just need to predict. We are not going to do calculation. We are not given all the answers anyway to do calculation. Pressure would increase, pressure would decrease, pressure would stay the same, can't determine. All right, let's see. Stored in a container with flexible walls at 15 degrees Celsius. Nothing is happening so far. Predict what would happen if the pressure of the gas happened to the pressure of the gas if volume of the gas is decreased. So what I would do a little drawing. This is the beginning. Suppose this is my balloon. And then what would happen to the pressure of the gas if the volume of the gas is decreased? So now the volume is decreased now. There, the volume is decreased. And the temperature is increased. What would happen if this is volume decreased? What would happen if the temperature is increased to the volume? Volume is directly proportional to temperature. Everybody should know that because this is your personal experience. It's not like you need to memorize that. Your brain already knows that. It's in there. Volume of a gas, if you increase the temperature, the volume is going to increase. So that's, you already know that. So if the temperature is increased, that means volume is increased. And so this volume is going to get bigger. I can show that by like that bigger. Now, we don't know how much bigger it's going to get and how much smaller we're going to get. If you would have numbers, we could calculate, but there are no numbers given. So in one part, the volume is decreasing by increasing the pressure, and the other part, the volume is increased by increasing the temperature. So therefore, these two are going to fight it out, and which one is going to win, we don't know because we don't have the exact number. Therefore, we cannot determine what would happen. The pressure might be increased before that. Maybe pressure would increase, maybe it would decrease, maybe it would stay the same. We don't know. Very likely, we don't know what would happen unless some numbers are given to us. Example 16. Assume 20 milliliter of pure CO2 is stored on top of the soda in soda bottle. A soda bottle has dissolved carbon dioxide in the liquid. And dissolved carbon dioxide is kept at a pressure of 4 atmosphere pressure. And on top of it, there is space, about 20 milliliter space. This is true for some soda bottle. And the temperature of CO2 is 7 degrees Celsius. It was kept in the refrigerator for a while, so the temperature decreased. Okay. And the pressure is 4 atmosphere. The 4 atmosphere pressure, that's a lot of pressure. That's why when you open a soda bottle, the gas escapes because it is under a lot of pressure. Calculate the mass of the gas on top of the soda bottle. What is the mass? How many grams of gas? Now, this is one of the questions where we have grams. So there is one equation where we have grams, and that's a particular form of ideal gas law. And that particular form of ideal gas law says PV equals nRT, but N equals grams divided by molar mass. So PV equals nRT and PV equals grams divided by molar mass. I'll put it in the parentheses so that I have easier time manipulating my numbers. N equals gram divided molar mass. R is the same and P is the same. So I write it down. Now, I have to find grams, so I have to isolate grams on one side, everything else on the other side. Gram equals, grams equal molar mass is going to be in the numerator. RT is going to be in the denominator. Grams, PV is going to be in the numerator. PV divided by RT. Okay, simple algebraic substitution, simple algebra here. So now I plug in the values. CO2, do you know the molar mass of CO2? Of course you do, 44.01 grams per mole. So 44.01 grams. Then I have multiply that by pressure. Pressure is 4 atmosphere, 4.0 atmosphere, 2 sig only, ATM. Multiply that with volume, 20 milliliter. It has to be converted into liter. 0.0
I can't see.
must be converted into liter because we have here this this volume is measured in liter. 020 liter. Divided that by, in the parenthesis, what do we have? R and T. R and T divided by R and T. So R is, which one you are using? We are using atmosphere, so we are going to use 0.0821 atmosphere multiplied by liter divided by mole multiplied by Kelvin. And that I put in the parenthesis. So make sure I understand that. And this is in the denominator. Okay, and then I'm going to multiply that with temperature, and that's temperature is given 7 degrees Celsius, 7 degrees Kelvin. So I'm going to multiply that with 280 K, and this I'm going to put in there. So now when I'm multiplying and dividing, I know what to do here. So start everybody multiplying and dividing here. 44 and 4 and all that good stuff. You do it so that you don't make that mistake that was made earlier, right? So that's why you do the calculation. I can calculate it too, but it's better if you do that.
You multiply 280 Kelvin altogether, right? Not just the denominator.
You are going to, this is in the denominator right here, this whole thing. So
Okay.
if you want to do that, multiply first 0.0821, multiply by 280, and then put it down in the denominator so that you don't make the same mistake again. Good. Okay. I got the answer and it's 0.15 grams. I only want 2 sig fig. You're doing fine with your calculator, then it should be 0.15 grams. All right. Now, take a 15-minute break and then you're going to start doing the experiment. And I'll be available, of course. So let's see, what time is it now? Oh, where is my time? 3:07. So let's make it 3:20. 320, we can start doing the experiment.
For some reason, I got the different answer.
Well, let's calculate it together.
Okay. So,
Okay, you tell me what you are doing.
okay. So I multiplied the denomination first, which is 0.021 times 280. And I got 5.88.
Okay,
And then for the top part, I did 44.01 times 4.0 times 0.020 equal to 3.5208.
mhm.
And I divide that by 5.88 and I got 0.59.
Unfortunately, I got rid of all that.
What was your denominator?
0.021 times 280.
It's 0.0821.
Oh, yeah.
Oh,
It's 0.0821 times
oh,
280.
821.
Very
Okay.
Yeah, yeah, that's why
That's
I was like,
the-
I heard that number weird.
That's the R, value of R. Okay.
Yeah,
R equals 0.0821 ATM. Oops, I don't want to do that.
So I don't know where you got 0.821.
This is where we got 0.821. Right there.
it's a formula that
Oh,
you need to know.
okay.
And we also did a problem over here. And we found out the R equals 62.4, 62.7, and we convert that into atmosphere, then it will be that. So either memorize it or write it down or know where to find it when you need it. The value of R is a constant. So a lot of people already did the experiments and found the value. And so we have the value already.
Okay, so atmosphere. So if it's torr, then it's 62.4. But if it's atmosphere then it's 0.0821.
And why? That is true. Why?
Uh,
Suppose the atmosphere 0.821, 0.821 are given to you. How would you convert it into torrs?
something about constant. I don't know.
How do you convert it into atmosphere into torrs?
You
How many torrs in one atmosphere?
I don't know.
760 by definition.
Okay. So
So we'll multiply by 760.
okay.
0.0821 atmosphere multiplied by 760 torr divided by 1 ATM. That would convert that into ATM, into store, and that would be 62.4 torr. Or simple dimensional analysis, changing the unit. All right. Okay, I'm keeping this. We're just gonna be here at 20 after. That's all.
Hey, Professor.
Yeah.
In the lab that was due yesterday, when calculating percent error,
Yes.
where do we find the true value? Because I have the value that we observed, the average from the 5.
Did I give you the true value? No. Therefore, you cannot do that.
Okay, perfect.
I'll have to do it. I had to find the true value and give it to, and then do it myself.
Okay, so I have it pretty much complete other than that true value.
Cool.
Do you want me to just submit it?
Yep.
All right, cool.
I also wanted to ask, are we calculating relative range or
Yes, you
don't-
are calculating relative range.
Oh, is it gonna be for the molarity or
Yes,
mean
it's
for?
gonna be for the molarity. You're right.
Okay, okay,
That's
okay.
the
Thank
final
you.
answer, right? Molarity is
Yes.
what we found, the final answer. And so we calculate those relative range and percent error, everything we calculate for the final answer. We don't calculate in the middle. Good question.
Okay, okay. Thank you.
Mhm. We're going to look at this video, gas collection. How is gas collection done? When a chemical reaction is happening and gas is formed, how do you collect that gas? It's just that. It's not going to be in the exam or anything. It's just a practical thing that is good for you to know. That's all. Collecting gas
What
by
is gas
displacement.
collection over water? We've got a reaction vessel here with a bung in to prevent gas escaping from the top. So it's going through the delivery tube and into this inverted measuring cylinder. And because the gas produced is less dense than water, you can see it bubbling above up to the top, and the gas is pushing the water down as it collects in the measuring cylinder. Now you can see the gas is above the water, so it's collection over water, and it's also pushing the water out, so it's known as displacement of water. The first thing to think about is the choice of the reaction vessel. One possibility is this sidearm boiling tube. We've got a fused glass joint here, and the delivery tube comes straight out of the side, and there's a bung in the top. Another option is to use a conical flask with a bung fitted with a bored hole through the center, through which the delivery tube comes out. Secondly, how will we secure the reaction vessel? There's two options here. We can either find a clamp and clamp our vessel like so, or another useful alternative is just to place it in a boiling tube rack like so. The choice of the collection vessel. And this depends on what you want to use the gas for. If you're interested in collecting the gas to use it, then if you don't have very much gas, you can use a test tube. Or if you've got a larger volume of gas, you can use a gas jar. That's so. However, if you want to measure the volume of gas, either the final volume produced, or you want to look at the volume of gas increasing over time in a reaction, then you're going to want something with graduations on. Most popular choice will probably be something like this measuring cylinder. Alternatively, if you want higher resolution, you can use a burette. Once you've decided on your reaction vessel and your collection vessel, we need to position the collection vessel. So I'm going to use one of these measuring cylinders, and you need a tub of water. About half full, this is just tap water, and this is where you're going to put your measuring cylinder in. I can, if I'm using something like a test tube, I can actually fill up my test tube directly from the water in the tub, just by tilting it upwards slightly, and then I've actually got no air bubbles whatsoever. This tub's actually too small to fill up the measuring cylinder that way. So I fill up the measuring cylinder from the tap. I filled it here right to the brim. But actually, as I look here, I can see that actually my graduations don't start until slightly above the base. Now, in order to get an accurate reading of exactly what volume I start with in the measuring cylinder, I'm going to just pour some away. Just a little bit. Now for the tricky part. I'm going to place my hand on top of the measuring cylinder, and then I'm going to invert it, making sure I keep good pressure on the measuring cylinder. I'm then going to put my hand under the water with the measuring cylinder and only remove my hand once I've got everything underwater. So now the measuring cylinder is in the water, we need to clamp it in place. We can use a clamp for this purpose. And we're going to just lift our measuring cylinder up ever so slightly to make sure that we can fit the delivery tube underneath. So once you're happy that it's in place, you can just clamp it. Check that it's vertical, that looks fine. Also check that you can read the scale. We can see the gas level is on the scale here, and we can read the scale. That will depend on where you're standing to do the experiment. Once you've done that, you can bring your reaction vessel. I've got the sidearm boiling tube here. And we just need to place the delivery tube snugly underneath. It doesn't need to go right up the tube. It just needs to go in so that the gas is definitely going to go in there. And we're ready to collect our gas.
Today, we're going to do
Okay,
a
we are not gonna
magnesium
see this.
hydrochloric acid lab. It's
That's
about
fine.
three things. It's about verifying.
Okay,
the
now
mo-
you are doing the experiment and I am available for questions. So that's where you are going. And that's all we are doing today.
Perfect. Sounds good. I love this.
So if I were you, I would just finish the experiment and do the write-up and be done with today. If I'm not here, just wait for a minute. I'll be back right away, pretty much. Unless I have to go somewhere, I have to, then I'll write down something, which is unlikely. When are the two people who wanted to come and get the guidebook too? When are they coming? When are you coming? I'm getting antsy. I want to see you guys.
Professor,
Yes.
so I think I can come on the weekend, like on Saturday. Then I'll pick the guidebook 2. Then I'll also have to come back for guidebook 3.
Yeah. How far do you live,
Oh, Tracy.
Captain? Oh, Stacy.
Tracy.
Are you going to come here for some other reason also?
Maybe, yeah.
Then yeah, then Saturday is good. Thank you.
Okay. All right. Thank
And
you.
it is, in case I'm not at home, it is outside and it's very easy to see where it's at. So you just pick up. There are both copies there, guidebook 1 and guidebook 2. So anybody's coming, you can just pick up either one of the copies if you want.
Okay. Thank you.
Yeah.
Professor,
Yes.
which lab is this?
We just talked about the lab in the morning, the same lab, that is the Boyle's law and Charles' law. Those two you're doing. And
Okay.
the third lab we don't have to do. It's not a virtual lab. It's just you have to answer some questions.
Okay. Are these due today, and is it in file?
They are not due today. I'm just saying that you could get them done today. Usually the labs are due 1 week after you do the lab. So we'll keep it that way.
Okay, thank you.
Uh-huh.
Okay, so these are the 5, 1, 5, 2, and 5, 4, right?
I don't know where the numbers you are reading from.
Oh, the lab
Yes, but where?
from I printed out the lab manual.
Yeah, that could be, but I don't remember them right now. It says Charles' law and Boyle's law.
Boyle's law. Okay.
And they are right by each other at the very end.
Yeah, Charles' law, and then derivation of ideal gas law.
Yeah.
Okay.
So what about the derivation of ideal gas law? Is it Boyle's law, Charles' law, or all three of those?
Good question.
three.
Yes. Yes.
All
Which
three
law,
of them.
which law is the boss law? Which law is the most powerful law? Boyle's law, Charles' law, ideal gas law, combined gas law. Which one is the most powerful gas law?
Which one's the what?
Most powerful, the boss.
The deviation of ideal gas law.
The ideal gas law is more powerful. Yeah, and then
Yeah.
you can derive all the laws from ideal gas law, really.
Okay, great.
I'm going to turn off the recording part. We don't need that anymore.
The recording has stopped.
And if you, I'm right here, so if you have any question, let me know. I can also share my screen if I need to. And if you, I hope you are getting this thing done. And if you have any other question, this is a good time to ask. Hello? Yes. Are you talking with me? No, you're not. Well, what? Huh? Yes, are you calling from Unions? Are you calling from Union City? Are you calling from Union City or not? Are you calling from Union City or not? So why do I see a number calling from Union City to me? Why not San Diego? Yeah, but why are you doing this? This is ingenious. Calling me with a phone for the phony number. I don't want to talk with you because you are calling me from a phony number. Bye bye. Sorry, folks. Phony numbers calling.
Did you try to get scammed?
No, I don't think it was a scam, but just anyway, let that go.
Hello, Professor.
Yes.
Oh, so I'm still a little bit confused with the molecular equation that you gave us for the lab. Like, how do we come up with the net ionic equation?
Yes. Did you balance the equation?
Yes.
Then you know how to write net ionic equations?
Yeah, I wrote something. I'm not so sure if.
Two things needs to be
Sorry?
converted into ions. What are those two things? When you are looking at a molecular equation, you want to break down two things into ions. Which are those two things?
Salts. Oh, I think like strong acids,
Uh-huh.
strong bases.
Uh-huh.
I think and salts too.
Right. Soluble salt, not just any salt. It has to be dissolved in water for something to be broken down.
Okay, okay.
And the H2SO4 is a strong acid, so break it down.
Yes, I did break that one.
Uh-huh. So which one you are confused about?
I'm confused about that AS2O3.
Is it a solid?
Yes.
Then are you going to break it down?
No.
No, because ions have to move and a solid ions cannot move, right?
All right. So like, yeah, as far as I have done the equation so far, I think that's the only one we don't break. Is it correct or I'm wrong?
H2SO4 would break, and KMNO4 would break, and K2SO4 would break, and MnSO4 would break. And the last one is the leftover is H. That one is a weak acid. So that will not break. H3ASO4.
Okay.
That one is a weak acid, so it would not break. Thanks for asking me. I should have written it down because I don't expect you guys to know that. But if you broke it down, I won't call it wrong if that happens, because I should have told you that. Okay, good. Thank you.
All right. Thank you.
We are very polite people. I thank you and you thank me. Wonderful. Very nice.
Oh yeah. Thank you.
Professor, I have a question.
Yes.
Who's your favorite student in this class? I mean, I know it's me, but I just wanna make sure, you know.
No, that secret I'm not willing to give out right now.
Come on, Professor. Let's hear it.
That's all right. We'll keep it between you and me
I had to keep some secret with me.
then.
So you do have a favorite. That's not nice to say.
I did not say that I have a favorite. You are
You
jumping.
said you're keeping it a secret. That means you have a
It's a
favorite. And you
secret,
keep it
meaning
a secret.
I have a favorite or not is part of the secret too.
She's just upset because she's not the favorite. Don't worry about it.
Oh, sweetheart. You keep on doing like things like that, I'll soon have a favorite student.
Professor, do you actually know the class average right now?
No, I don't.
Okay.
And this class, you get your grade according to what you do. 90% is an A, and it has nothing to do with anybody else. So I don't do curves. Everybody, one of your graph is going to look like this. Look at that. Nice curve. Some other graphics are going to be straight line. So be mindful of that. When is a graph a straight line? That's a good question. And if it is a straight line, you are supposed to draw a straight line, best straight line. If you are doing on the computer, you should ask the computer to do a straight line. If you are doing it by yourself, you should take a ruler and do a best straight line, and you should know what does that mean if you are doing it by hand. And if it, in this case, it is going to be a nice curve, some of them, and some of them are straight line. Why is it a straight line? Because when something is directly proportional to something else, then it's going to be a curve. But if something is inversely proportional to something else, it could be a straight line. Think about that. Those are the two things. We have directly proportional. Volume is directly proportional to temperature. And in that case, is it going to be a curve or is it going to be a straight line? And pressure is directly proportional to pressure is inversely proportional to volume. In that case, is it going to be a straight line or is it going to be a curve? And if it is a straight line, do not make a broken straight line. It should be a straight line all through. And one more thing I found for maybe one or two students looking at their graphs, a big mistake in graph is to have different values for a line. For example, different values for a line. So, for example, how can I say this? I'm gonna open up share my screen and show you what I mean. I want to make sure that you don't make that mistake. Only I think one person made that mistake, and I told them that please don't make such a mistake. So this is our graph. I am going to annotate and draw and get a straight line draw. Yeah. Okay. And then lines are like this. You call this 2 milliliter. You call this 2 milliliter. You write down volume in milliliter like this, V ml. Then you don't have to say 2 milliliter, 4 milliliter every time. 2, you call this 4, you call this 6, and then you call it 12. I can't do that. Each line is only 2 milliliter. So this 6, this should be 8, not 12. But there is one person at least who did that. So be mindful of that, please. This is 8 and 10, and like that, it keeps on going like that. Don't jump. Okay. Graph has a title. If you don't have a title, I take away points. And you have to tell me the units. Either you write the units like that, or you write your unit after every one of them. Either way is fine. This is better, of course. If this is pressure, then pressure P in atmosphere, P ATM, like that. And you just have to do that. You don't have to have a arrow going that way. I would understand what that means. Arrow is better, but not necessary. So either a graph is going to be a straight line like that, a straight line, sorry, not measure, or it's going to be something like that, a nice curve. To decide which one it's going to be and do it right. Okay, any questions? I hope you are doing this. And if you have a question about the other lab or something, let's get out and let's take care of that too. And is anybody going to see me at 5:30? Probably not, but it would be good for me to know if you're going to see me at 5:30.
I'm not going to be there at 5:30 today, Professor.
Thank you.
Neither am I.
Okay. Probably nobody, because you have the time right now. So why don't you take care of things right now instead of 5:30? So that would make sense to me. I'll be there nevertheless because I committed. I have committed. So that's a question of my commitment. So I will be there. Okay, I'm going to stop sharing screen, but anytime I can start again. So just let me know. Ah, ah. Everybody is doing fine. No questions about this lab. All right.
Hey, Professor, I've got one more question on the standardization of potassium percarbonate.
Yes.
Does the can you explain if the H3, the 10H3 ASO4, if that breaks down, or is that
Don't
in
separate
the
it down.
in the ionic equation?
Do not separate it down in the ionic equation.
It stays together.
It's weak acid.
Ah, it's a weak acid. Oh, that's right.
No, I didn't tell you that, so I'm sorry.
That's okay. And it's aqueous, right?
Yes.
Okay.
After chem, just utameta library physics after chem. Copies za class 440.